Couple of items. I looked at the polls. Majority of you have chosen before the before the spring break for the date of midterm. So we will have it on the Friday just before the spring break, and we will cover all the topics from the first lecture until whatever I'm going to be doing just before spring break. All right, so it'll be the fundamentals of mechanics, fundamentals of power electronics, and then the electromagnetics theory. Before spring break, we might get one lecture or two lectures of machine design, a little bit DC motors, but that won't be covered in that won't be part of the midterm. Right. So as far as the exam is concerned, it'll be basically whatever we cover in the homework. If you're quite comfortable with the homework and you understand everything, you should be able to do a good job on the midterm. Typically, the midterm grades, the highest last time was like 70 or something, but I will normalize it. So whoever gets 70 will be normalized to 100. So once you're done with the exam, don't feel too bad if you're not able to get through all the questions. It's very difficult to get through all 4 questions. Just do your best attempt, and that's pretty much it, right? Everything is allowed for the midterm. You can do whatever you want. Those of you who have DRC requirement for additional time, I'm not sure if this classroom is available past the classroom time. So please reserve a room with DRC so that you have a quiet environment where you can take the exam comfortably. Right. As far as the polls were concerned, most of you seem to understand what's going on in the math. We are going to get a little bit more advanced into the math after 4 3 weeks. It'll start to get easy again once we go through these topics. But the primary reason I record the videos is so that you can always go back and look at the video again if there's something that you didn't completely understand in class, and you can always come back and ask me after hours as well if you want me to explain something in more detail. A couple of you had mentioned that I don't mark the equations clearly enough. I'll try to do a better job going forward, but at any point, if you don't understand any terms that I put on the board, just stop me, right? Just call my name and, I can clean it up and explain it better. So whoever thinks it's not well explained or anything, don't hesitate to stop me at any time. And one of you had mentioned that the textbook content is slightly different than what's being covered in the class. I'm surprised some of you have gone back and looked at the textbook. I thought nobody can read those chapters, but so the way the textbook is written, the textbook was written like about 20 years back when there were not many power programs offered in US, and it was a very big problem. So Professor Mohan, when he wrote the book, the objective was to make it more accessible so that more faculty would be inclined to teach the course. But that also means it doesn't cover a lot of topics that are very critical, with detailed subject knowledge and stuff. So we are going to take whatever content is there in the textbook, but go much, much deeper than what's there in the textbook. All right, the textbook is very helpful if you already know the subject and you just kind of want to brush it up, like a couple of years down the line, you want to go for an interview and you want to remember things. That textbook is the best textbook to have in your shelf because it's very easy to understand and you can quickly get through the content. But it's not particularly very good for the fundamental topics. All right, so we are going to be covering all of those in detail. As far as exams and homeworks are concerned, it'll be more towards what we cover in class. We won't put too much attention to what we do in the textbook. One of you had asked for additional homework examples or more examples. The textbook would be a good avenue to look at all the example problems, right? In addition to whatever we do in the class, there are more equations and examples given in the textbook which you can go back and look at. Usually in the beginning, first 2 3 years of undergrad, faculty will do more examples in class and to tone down the theory. But once you get to an advanced course, we do more theory in the class and then do homeworks and stuff on your own time so that we don't waste time on doing simple numerical problems in class. But as and when it's necessary, if the content is too difficult and an example will make it better, then I will go through that example. But otherwise, we are going to keep a little bit check on how many examples we do in class. Somebody asked about a practice exam. There won't be a practice exam. All the homeworks are pretty much the practice exam that you're doing. So questions in the exam will be exactly whatever is in the homework, just a little bit more complicated, just a little bit more difficult. Right? Then clearly mark the equations that I think I've addressed it. Otherwise, some of you had said that I'm going a little bit fast. Most of you said the pace is okay. You're satisfied with it. As far as the prerequisite, so these are all prerequisite content that you would have likely covered in your previous courses. That's the reason I'm trying to keep a decently moderate fast pace. But once we get to new content, which I haven't covered before, like once we go to motors and machines and torque and all of those, I will go much, much slower than what I'm going at, right? But again, all of these videos are recorded, so you can go back and play the video again and take a slower look at it. But again, at any point, if I go too fast and you feel like you haven't understood the concept, do not hesitate to stop me, right? You don't have to go and wait till go and see back the video to understand the concept. If you don't understand anything in the class, just stop me right away. It doesn't matter if it's just one person who doesn't understand, everybody else understood, I'll still go over the content and explain it. So don't hesitate to stop me at any point. And if you stop and ask me to explain again, that counts as in class participation too. So, that's an excuse to stop me more often. Okay, anybody have any questions? Okay, I haven't taken a look at the homework. After class, I'll go and take a look at all the homework that I've been submitted so far. If there are any minor mistakes, I'll post a comment. Or whoever has submitted, even if you don't have any mistake, I'll post a comment saying that I didn't find anything wrong. So later tonight, check. If you don't see any comments, let me know. If you're already submitted by now, and if you don't see a comment later tonight, let me know. Because I think there's some odd Canvas setting where the scores don't display until the due date passes or something. So if you don't see a comment, let me know. So just a quick refresher. We are going to look at what we covered at last class, and then we are going to derive a couple of more equations in this lecture. And then the next week we'll continue with the same thing. So we'll have 4 to 5 lectures of electromagnetic theory, and with that we'll be done. So last class we're looking at the 5 Maxwell's equation. The first one, divergence of electric field equal to the proportional to the charge density enclosed, and then the curl of the electric field is the time rate of change of the magnetic field, which is basically the Faraday's law in a different form. And then we have the Gauss's law for magnetism, which is divergence of a magnetic field is equal to 0, that is there are no magnetic monopoles. And finally, the curl of a magnetic field is proportional to the current density, which is the Ampere's law. And then the other additional component which was introduced to explain the displacement current, basically the current that we observe in a capacitor. So if we have a capacitor and current is flowing through it, we put a magnetic sensor of some sort, we can still measure a magnetic field. Right? So the first component alone won't explain, because in the traditional sense of current, there is no charge moving through the capacitor. But we still measure a magnetic field because of this component. And the final equation, so these are all the 4 of the field equations. But the real world effect, the force, comes in the final equation, the Lorentz force equation, which is basically force equal to Q times E plus V plus V, right? And for our case, if you don't understand, so I have defined what divergence and curl are here. You would have learned this all from vector calculus course. But for our own course, these notations are not particularly helpful or useful for us. Because when we go to 3D radiated fields or something like that, it's very helpful to have it in those notations. In our case, we'll always resolve it into a 2D planar surface, in which case representing in form of surface integral or loop integral, those are much more we'll be going forward in the course. So we're going to use these 2 theorems, Gauss's theorem and Stokes' theorem, to reduce the beautiful forms of equation that we have into a much, much simpler form that we can handle going forward throughout this lecture. So if you really don't know what divergence or curl is, that's absolutely fine. You'll get through fine with this course, no issues at all. But if you're interested in getting a more intuitive understanding, even those who have done vector calculus might not have an intuitive feel for what these 2 terms mean. I posted a video on Canvas of this channel called 3 Blue 1 Brown, a brilliant math channel. And there he explains basically, gives a very intuitive feel for what divergence and curl are. So I'm not going to repeat the content. But those of you who are interested can go check it out. But for our own course, it's irrelevant. So so the Gauss theorem states if you go over a surface, closed surface, integrate the vector field, it is going to be equal to the volume integral of the divergence of the vector field. In the Stokes theorem, if you go over a loop and integrate the vector field, it is going to be the surface integral of the curl of the vector field. Right? So we are going to employ these 2 theorems to reduce these 4 equations that we have on the top there. So the first equation that we reduced last class. So the first equation that we reduced last class was the equation 1, which the divergence of the electric field is proportional to the charge density enclosed. And plugging it into the Gauss's theorem, we have this simple form where if you go around a closed surface, right, it's very critical that the surface is a closed surface. If you go around the closed surface and integrate the electric field, it is going to be equal to the charge enclosed divided by epsilon naught. Right? So we looked at the case of a point charge and we enclosed it with a sphere. And we said that we are going to assume that the electric field is radial at every single point. We'll clarify why it's radial at every single point in a minute when we go to the third part. But then if it's radial at every single point and if the charge is centered in the sphere, there is no reason that the electric field at every single point is going to be different. So it's going to be all same at every single point just because of the symmetry that the electromagnetic theory law follows. Right? So given that when we have this expression surface integral E dot ds equal to q enclosed by epsilon naught, we are able to take the electric field term outside because at every single point it's exactly the same. And E dot ds, so that means the dot product. So if we have a surface like this, if our electric field is perpendicular to the surface, then that's absolutely fine. E dot ds is just same as E ds, right? Magnitude of E times the surface area, whatever you consider. But if you had a surface area like this, but then the field was not in a perpendicular direction to it, that E dot ds term is the dot product, right? So the vector of an area is perpendicular to the surface area. So you need to resolve this into a component that's perpendicular and the component that is tangential to the surface. So the perpendicular component is what matters. So E perpendicular times the surface area, right? So in our case, we are going to assume it's radial. That means perpendicular to every point on the sphere. That's why we're able to just take the E magnitude alone directly outside without considering a perpendicular or tangential component. And then once we take the E out, the surface integral of a sphere is just 4 pi r square, and we got the electric field S q divided by 4 pi epsilon naught r square. And the rest of these are just miscellaneous. Right? If you look at the force equation, go back and plug it into the force equation. If you introduce another charge in the electric field, you get our Coulomb's law, which was Q1 Q2 divided by 4 pi epsilon naught r square. And then the other thing we noticed is we looked at it for a case of a charge centered around the sphere, at the center of the sphere, but we can put this charge at any odd place in the sphere as well. Right? If you put it in any other odd place and go around and still integrate the electric field, you would still get the same expression that it's equal to Q enclosed by epsilon naught. And we try to get an intuitive understanding for what was going on. Basically, when the charge is closer to this side, this cross-sectional area becomes smaller by a factor of r square, while this cross-sectional area increases by a factor of r square. Right? Well, the electric field here reduced by a factor of r square inverse, and here it increased by a factor of r1 by r1 square, again inverse. Right? So both of these terms will cancel out. So effectively, if you go around, it will still end up being q divided by epsilon naught. And then the third thing we addressed is why did we choose this kind of nice smooth spherical surface instead of looking at this very odd shape? And James gave the answer, where if you look at this kind of odd shape, it becomes very complicated to do the integral, right? Because not that the surface is complex to integrate, it is that the electric field at every single point for the surface is not known. Right? Here we could assume it was all constant. Here we can't do that assumption, which makes this solution far more complicated. Right? So this is the first equation that we reduced. So the first one goes away. We no longer have to remember this. It is just surface integral of electric field equal to Q enclosed divided by epsilon naught. Any questions? So the second set of equation that we reduced, was equation 3, which is basically the divergence of a magnetic field equal to 0, no magnetic monopoles, which was the third equation that we had there. So again, plugging it into the Gauss's theorem, same Gauss's theorem that we used here, we are going to use here as well. If you go around a closed surface and integrate all the magnetic field, it's going to be equal to 0. So what that essentially means, whatever field lines leave out, equal number of field lines enter back in. Or another way of stating it is the flux leaving the surface on one side must be equal to the same amount of flux entering the closed surface on the other side. Right? So we are going to define a new term, flux, which we haven't done before. So this is purely a definition, right? Not a law or anything. So we are going to define a flux which is equal to the surface area of the magnetic field. If you do it over a closed surface, this is not a closed integral. If you do it over a closed surface, the net flux will always be 0. If you do it over any open surface, that is just a regular flux. So if you have like an area like this, and if I have a B field again perpendicular to it, if it's not perpendicular, consider only the perpendicular component. And let's say this is some cross-sectional area A, and if the B field is constant, then the flux equal to surface integral B dot ds simply resolves to B times the cross-sectional area A. Okay. So the other name for magnetic field B is the magnetic flux density. That comes from the fact that it's flux per unit area. Right? So one of the units for magnetic field is Tesla, There's Gauss and Oersted, other units as well. We'll always look at Tesla. The other way of representing magnetic field would be Weber per meter square. The units for magnetic flux is Weber, right? Or you can otherwise say it as Tesla meter square. Okay, so that's the third equation that we reduced. So let's remove that and replace that too. So this goes away as well. We now have a simpler form where we are going to define a new term, flux. This is the surface integral of B dot ds, and flux over a closed surface is going to be 0. Right, with that, we don't need Gauss's theorem. Both the divergent terms have been eliminated. Right, so we can forget about this. So next, what we are going to be reducing. So we remove all of this, remove all of that. So we have two simplified equations going forward. The third equation that we reduced was the equation 4, which is basically the curl of the magnetic field is going to be equal to the proportional to the current density plus the rate at which proportional to the rate at which the electric field is varying. So here are two simplifications that we carried out. The first one is that this 1 by c squared term is extremely small because c is very large, pushing this whole product towards 0. And the other thing is that the rate at which electric fields change in a motor is very tiny, right? Because the rate at which these motor frequency changes, the rate at which the terminal voltage changes in case of an AC motor, let's say, is going to be at the fundamental frequency, like 60 Hertz grip frequency. Or if you have a drive connected to it, it'll probably be like 100 or 200, 300 Hertz, right? Which is not too much. Typically, when you have electric fields varying at gigahertz, that's when you'll have radiated fields, like you have your antennas and radio towers and stuff like that. So our frequencies are so low and our voltages are pretty small too, compared relatively. So this whole term is very tiny compared to the fields created by the current, magnetic field created by the current. So in our case, we can assume this term to be 0. Again, when you do research on motors where you want to look at common voltages and stuff like that, this term plays a very prominent role, can't be ignored. But for our case, for understanding the torque production of a motor, this term is completely irrelevant, right? So we are going to delete that out. It doesn't play a role for us. So we are left with curl of a magnetic field is equal to mu naught times J enclosed. And the term, if you want to analyze radiation without the term, you can't explain the radiated field, right? In our case, we won't look at it. So curl of a magnetic field is just a second, sorry. So curl of a magnetic field is proportional to the current enclosed. Is proportional to the current density enclosed. So using Stokes' theorem, which is the last one, we can rewrite it in a form that surface loop integral of a magnetic field is equal to the surface integral of the curl of the magnetic field. Plug in those values, you end up with mu naught times I enclosed, because surface integral of current density is basically because current density is just a component of current that's perpendicular divided by the cross-sectional area. So the current itself is the current density times the cross-sectional area. Right? So surface integral of current density gives you the current enclosed. From here on, we use this principle to figure out what the magnetic field is going to look like for a current carrying conductor. Right? So if you have a current carrying conductor, you can use a simple thumb rule. Basically, you have a current carrying conductor, curl your right hand around the conductor so that the thumb is facing along the direction of the current. However your fingers curl, that is going to be the direction of the magnetic field. So if the current direction was flipped, the magnetic field would become clockwise. In this case, if it's going up, it's going to be anti-clockwise. Again, this is purely just a convention. You can go ahead and create a whole new way of representing it by putting it in the opposite direction. It'll just confuse the heck out of everybody, but you'll be absolutely correct that there is nothing wrong with whatever direction you choose. But all of us have settled on this direction, so we're going to continue with this direction. So if you go around the loop and integrate this magnetic field, we have this formula. It's going to be equal to mu naught times I. Now again, the same assumptions that we made about the symmetry of an electric field, we are going to make about the symmetry of the magnetic field. At every single point, we are going to assume the magnetic field is going to be the same if it is equidistant from the conductor. There is no reason that magnetic field here should be any different from the magnetic field here, right? Because if you rotate the whole thing, there should be mirror symmetry of this whole, there should be symmetry depending on irrespective of which point you look at it from. And the other assumption we are going to make is that the B field is purely tangential. Right? There we assume the E field was purely radial. Here we are going to assume the B field is purely tangential, and we'll explain why that assumption is true in the end, okay? So if B is only tangential, then we can go around and integrate the B field, right? So it's tangential at every point. If it was not tangential, then we'll have to resolve it into a tangential component and a perpendicular component and only integrate the tangential component. But in this case, it's only tangential, so the whole term is just whatever the term is. So you can pull the D out, integrate over the loop, that is just the circumference of a circle, 2 pi r, and then you end up with the magnetic field equal to mu naught I divided by 2 pi r. So here again, it doesn't matter whether the conductor is right smack in the middle of the circle that you've chosen, or it's at some odd corner here. In the same case again, here it will be 2 pi r1, with r1 being this side will be 2 pi r2, with r2 being a much larger radius, while here the B field is inversely smaller by a factor of r2. The area over the distance over which it's integrated is proportionally larger by a factor of r2. So the product would end up being such that it's always equal to mu naught times I enclosed. Right? So the same principle that we had there it was area, here it's just distance. So the reason why our assumption that the tangential field, the field is tangential always is true is because if it is not tangential, so if I had a current carrying conductor and I had a magnetic field, and let's say there it was not tangential, but it has components like this. Right? I can always draw a surface where multiple field lines enters, few field lines may exit, but on a total, there might be effectively more field lines entering than more field lines leaving. Or it could be the other way around, right? More field lines leave the surface compared to field lines entering the surface. Which is problematic because that will violate this law that flux over a closed surface must always be equal to 0. All right. So the only way that can be satisfied is if the field lines are always tangential to the surface. It's a closed circle that I've drawn there, right? So we can do the similar extension and go back and explain why the electric field must also be purely radial and not tangential. Because when we consider an electrostatic case, by electrostatic I mean where the electric field is not changing, your charge is not moving, your charges are all static. Right? If there is no moving charge, the electric field is not varying over time, so the dE by dt term is 0. And if there is no moving charge, there is no current. Right? Current is dq by dt. So if there is no current, there is no magnetic field as well. And again, there is no magnetic field because the second term is also, so the I term is missing, and then dou E by dou T term is also 0. So that's what the definition of an electrostatic field is. In an electrostatic field, if you look at the second equation, the curl of the electric field must be equal to 0. Because if B is 0, dou B by dou T becomes 0. If the curl is 0, then if I go around the loop and integrate the electric field, right, that term must end up having to be 0. And that cannot be 0 if it is not purely radial. If there was some tangential component, I can always create a loop over which I can go around and integrate the electric field, and it will end up being non-zero, which will violate the second law for electrostatic field, which is that the curl of an electric field must be equal to 0. All right. So that's the reason why if you go around, in that case, it was purely radial for an electrostatic. Now, if I had a magnetic field in this case, in the second first case, and there was a varying magnetic field that was creating some electric field, there is no reason this electric field has to be radially outwards. Right? For instance, when we draw the waveform for light, we have this electric field and then magnetic field which is perpendicular to it, all varying sinusoidally. None of it is radial from any charge or anything. Right? In those cases, we can have complicated structures for electric field, but this is only applicable for electrostatic field. Right? So that's just a quick overview of what we covered last class. Anybody have any questions? Do you want me to repeat anything? Right, fantastic. So let's continue with today's derivation. So there's one equation that we haven't managed to reduce, which is, so this is also reduced. Which is that if I go around the loop and integrate the magnetic field, it may be equal to mu naught times I enclosed. There's a particular reason I'm carrying on this I enclosed. There's a very specific meaning to it. For now, it's just the current through the conductor, but it is not exactly the same as the current through the conductor in all cases. Right? But for now, you can just think of it as a current in a conductor. Okay, so we have reduced 1, 3, and 4. Now let's today try and figure out how to reduce the second equation. So for this, we are going to use a example that's very commonly used in all electromagnetic, at least modern day electromagnetic theory textbooks. And the provenance of this example, I was able to trace it back to Feynman's lecture. I don't know if that's the earliest instance where this example was used. But so we're going to look at this U-shaped bar on which there is a metal rod that can move around. So think of it like a bike lock. Right? When you have a bike lock, you have this U bar over which this locking mechanism can move on and off. So it's the same thing here. So this is a fixed rod, and the length of this rod is variable. So where this bar is located, that bar can be moved around on this rod. Okay? And the width of this bar, this is not going to change. This is fixed. And there is some magnetic field going through this bar, coming out of this page. Right? So we're going to introduce two symbols. If I use this dot convention, so what this dot means is the B field is coming out of the page, of the surface. Not just for B field. Like if I want to draw a current carrying conductor that basically is, let's say a current carrying conductor is going in this direction, coming out of the page like this. If I want to draw that, and if the current is coming out towards you, then I would use this convention. If the current is instead going into the page, right, you draw the cross, which is basically going in. So the convention basically, if you curl your hand around it, the thumb is supposed to indicate the point. The cross is basically when you curl the little finger, there is a cross that's formed in your skin fold. That's basically what the cross is coming out of the symbol. Right? So out of the surface, into the surface. So we have some magnetic field coming out of the surface. So think of some magnetic, something is creating this planar magnetic field. We're not worried about how it's created. It could be a magnet there. And then we are basically putting this U lock, bike U lock on top of this. And what we are going to now start doing is move this rod around, and we are going to measure what the potential is developed across this. All right. So all of you would have learned about Faraday's law in your high school. That is not the same form that we have there, written there. Anybody remember what was the form you learned in your high school? Yeah, I said.
V of rho is rate of change of flux.
Okay. So E equal to d phi by dt. Is there anything else missing?
Sign and
Signs.
number of turns. That matters.
Okay, number of turns. For now, we are looking at only one loop, so let's not introduce the end term. Right, we'll get to the end term though. So there is a number of loops to keep in mind. So this is the Faraday's law that you have learned of. Prior to taking an electromagnetic theory course, right? So it's also called the Lenz's law. An Estonian physicist, back then was part of Soviet Union. Russian Empire, not Soviet Union. So the Lenz law basically tells you what the sign of this EMF that's generated due to this varying flux is going to be. Right? I'm introducing a lot of terms here because I haven't defined what EMF is. Right? It's a new term we are bringing in, and I said I'll never bring a new term without giving a reason for it or deriving it or defining it. So we will do all of those in a minute. But this negative sign basically tells what the polarity of this EMF that is generated is due to the change in the magnetic field, due to the change in the flux. Faraday's law itself just tells the E is proportional to the rate of change of the flux. It doesn't give a polarity for it that was given by the Lenz's law. For now, we are not going to be too worried about what the negative sign means. I myself particularly keep forgetting what the negative sign actually means whenever I go and draw back the circuit. But there is a much more easier way of intuitively figuring out what the sign of the polarity of the voltage is going to be. Because the negative effectively doesn't say whether I put a negative here or negative here, right? So it's much better to understand the theory of it and then intuitively put a sign where it needs to be rather than trying to remember a formula. Okay. So let's substitute into this equation. But Our definition for fluxes, we have already defined. So this is EMF, electromotive force. Again, we look at why it's called EMF, why it's electromotive force in a second. But so we have already defined flux as surface integral of the magnetic field. So surface integral not over a closed surface. If it's over a closed surface, EMF will be zero. So surface integral of a magnetic field. So minus d by dt. Here I'm not changing the magnetic field, it's a constant magnetic field. B is fixed, right? Not varying. So that means I can just pull it out, even out of the differential. Or no, I can at least pull it out of the integral because across the surface it's a constant magnetic field that is not varying across the surface. What would this integral come out to be?
Is it just W times L?
W times L, thank you. So we have d by dt times B times W and L. Can I pull all of these terms out? Which one can I not?
L.
L. And what will the differential of that be? What was it?
It's just velocity.
Velocity. So that's just going to be the velocity with which the bar is moving. So let's define the velocity as V. So this is just BW times the velocity V. Let me write it on the top. Oh, negative sign. Again, if I miss the negative sign anywhere, don't worry about it, stress about it. We will figure out what that negative means in the end. So, so our EMF E. So this is not the electric field. I use the tiny E for EMF. Maybe negative V times W times the velocity V. So this law that we have written, this Faraday's law E equal to minus d phi by dt, that is not a fundamental law, right? None of our equations there is equivalent to this one equation that we have here. So we need to map this back to one of those 5 equations there. So those are the 5 set of equations that encompasses all of electromagnetic theory. Anything else if we introduce, we have to map it back there because we can't randomly just define a new equation and say that that's the new law or something. Okay, so let's try and map it back to that expression there. So let's go back to this case here. So we have some magnetic field perpendicular to the surface. And we have some rod moving with some velocity v, right? And we are going to assume this rod has some charges, q, positive charges that are free to move around. And when the theory of electromagnetic, all these work on charges, moving charges and magnetic field due to them were created, it was much before the atomic model was known. Right? Atomic model was later part of 19th century, early part of 20th century. This was all in the early part of 18th century. So atomic model was known and it was assumed that the positive charges moving was what was causing the current. Now we know it's the free electron cloud moving in the metal is what causes the current. But we're going to go with the model where the positive charges are moving because it will be easy for us to indicate the direction of current as same as the direction in which the positive charges move. All right, that's not how it works in reality, but we are going to stick with the assumption. So we have some positive charge moving with some velocity v in a magnetic field B, which is coming perpendicularly outwards to the board, right? So when I draw this dotted, it's coming outwards to the board. What is going to be the direction of the force? Upwards, downwards?
Downwards.
What was it?
Downwards.
Downwards, perfect. Right, so curl your hand from B to B, right hand, whichever direction your thumb points, that's going to be your direction. It's always counterintuitive to do it when it's downwards. So what you can do is curl your hand from B to B instead, right? It should be from B to B, but curl your hand from B to B instead and just flip the direction of whatever you get. So at least I find it difficult to visualize it in a flipped manner. So just flip the law around and put a negative sign, right? So this is going to be the direction of our force. So these charges are going to be experiencing a force that is pulling them downwards, right? So let's Let's define another term, charge density. This is the number of charges, not the magnitude of the charges, just the number of charges per unit length. Right? Let's say this bar has 500 free positive charges that can move around. Then this knob and the length of this bar is 2 meters. Then eta L would be 500 divided by 2, which would be 250 charges per unit length. The magnitude of the charge itself, if it's let's say a complementary pair of the electron, then the charge is going to be positive value of whatever the charge of the electron is going to be. So the total charge in the bar is going to be equal to Q times eta L times what is going to be the total charge across this bar? There's still one more unit missing here. Okay.
The length of the bar?
Okay, the length of the bar. Somewhat counterintuitively, I've labeled as a W instead of using L. But so that's going to be the total length of the bar, which is going to be W. Right, so that's the total charge on this bar, and all of these charges are experiencing the force because it's moving in this direction, and in the presence of a magnetic field, it's going to experience a force that's perpendicular to both the B field and the direction in which it's moving. So that force is going to be equal to total charge times the B field, the velocity times the B field. Since V and B are perpendicular to each other, the way I chose it is perpendicular. So the cross product just resolves into the product of the magnitudes alone. So this is just Q eta L times B times W times V. Okay. So I can rewrite this such that it's force divided by Q eta L is equal to V times W times V. Now if you look at the RHS, ignoring the negative sign for a minute, the RHS of this term was the RHS we derived in the previous case using the Faraday's law that we know from high school. Both of those RHS are the same, right? So whatever we have on the LHS is going to be our EMF E. So what is this term effectively saying? It's basically the force experienced per unit charge, total charge per unit length. Right? So it's charge per unit length. So let's say this is a distance of 1 meter and find out what all charges are there. Whatever force is experienced by those charges, that is effectively going to be your EMF. So it's force experienced per unit charge, or basically the force that moves an electron, right? And hence the name electromotive force, right? Why don't we just call it potential? Anybody? Why don't we just call it a voltage? Why do we have a new term called EMF? Anybody? When can you use the term potential?
A difference.
It's a difference, but whenever you have an electric field, you can't always use the term scale. Is potential a vector field or a scalar field? Scalar field. So again, going back to your vector calculus course, you would have studied where if you have a vector field where the curl of the vector field is 0, then such a field can be represented as an equivalent divergence of a scalar field. Right, so that's why the electric field is basically the divergence of voltage potential. So if the voltage here is 100 volts, the voltage here is 0 volts, then across this the electric field is going to be 100 minus 0 divided by the distance dl. Right, so dV in case of 1D, it's going to be dV by dl. This is just basically 3D case. It's the voltage divided by the x component, and the variation in the x component, y component, and the z component. Right? So, but this is only applicable if our curl of the electric field is 0. In our case, the curl of the electric field is not always 0, right? Because going back to our equation, when we have varying magnetic field, this curl is not zero. If the curl is not zero, then your electric field cannot be represented as a gradient of a scalar potential field. All right, so E equal to divergence of a scalar field B is no longer applicable if this dB by dt term is not equal to zero. Right, so we cannot anymore represent an electric field that is varying, that is being created by a varying magnetic field as purely a divergence of a potential field, and hence the reason, as we will see, this voltage EMF can be created by not only this bar moving, but also this magnetic field changing. Both of it can create that EMF. So we cannot directly go and just call this term as voltage, because that will be counter to what voltage, scalar potential voltage was defined earlier. Right? Yeah, please.
Is there a reason why the bottom equation for EMF doesn't have the negative, while the one that we originally wrote does?
Yeah, I'll get to the negative sign in a minute. All right. So the way we derive this, the fourth direction, that is basically what the negative sign here is indicating. This we just defined it with the negative sign. Here we are deriving it, but I'll give an explanation as to what the negative sign is doing in a minute. You had a question?
So I have one more question. And you said that the negative sign shows if it is polar or not? Like it shows its polarity?
Yep.
Okay.
Yeah, I'll put what the polarity means in just a second.
Okay.
Any other questions? Ben, you have a question? There are no wrong questions.
What exactly is going on? So like, you said there's a bar and a rod, or are there two rods? Like, what exactly is going on in the
So
diagram?
you've seen the U lock for a pipe, right? So this U is basically the U of the lock, and then this bar is the one that can move around. Okay, so think of it, I should have brought so think of it like a U, and then you have some holes on the bar so that the bar can move through the vertical two metal lines. Still on.
So which one is like lock? Is it the vertical one or the horizontal one?
The
Which
word, this was the one through which you put the key and lock. Sorry everyone, due to some laptop issues, the recording for the second half of this lecture didn't come through. So I'm re-recording this content, whatever we covered in class, right after class. So some of the questions that you asked during class will not be there in the second half of it. But as much as I remember, I'll try to address them in the re-recorded videos. If anything I missed, just let me know on the Canvas discussion page and I will reply to them. All right. So once again, this is just a re-recording of what was covered earlier today in class. So the point at which the laptop cut off, Ben was asking the question about more clarification on the structure of the setup that we have here. So what we have here is basically a U rod, right, with the open space in between. So this is a solid rod. It can be of any material. It can be wood, it can be iron, any conductive material or non-conductive material, right? And then on this rod, there is on this U structure, there is another rod which is free to slide around while making electrical contact. Right, so this again is a solid bar. And this bar can move around. And then there is magnetic field that is coming through this surface. So think of it like a slot inside, and through which magnetic fields are coming out of it perpendicular to it. Right, and the setup is set on top of it. So the way you can imagine it is you have a piece of paper. So I have this piece of paper here. Let's think that there is a slot inside here, right? And there is a magnet underneath the slot, and the magnetic field is coming from the bottom and coming out of the top, right? In a planar form as indicated here. Okay. The only difference is there is a rod here that can move inside and outside, changing the surface area that we have here. Right. Okay, so the second question that was asked again by Ben that got cut out of the second half of the video is whether this item has to be a conductive material. It does not. It can be any material. In fact, you don't need a material there at all. We can just have a rod alone. And if this rod is moving around in a magnetic field, the charges there is going to experience a force. And in turn, it's going to get separated out with the positive charges going to one side, negative going to the other, effectively creating the EMF that we are seeing over there, right? So there is nothing about the material of this bar that is indicated by the equations that we have written so far. None of the equations there has anything about material property in it. It is independent of whether you have a material here, whether you have a loop here, you don't have a loop here, it doesn't matter. If there is a magnetic field and you have a bar that's moving through that magnetic field, it's going to experience charges on those are going to experience a force. And if they are free to move, they get separated around. These hypothetical positive charges come to one side, or effectively just the negative charges accumulating on the other side, effectively creating a voltage potential difference, which is then going to be measurable. And if you connect a conductive bar, that is going to cause a current to flow through the conductive bar. All right, that's about it. But the conductive bar is not essential for the EMF to develop in any way. Okay, so let's continue with the second part of it. So the second section, what we are going to look at is the length is fixed. That is, this rod cannot move around, but this magnetic field is varying. All right. So in this case, the Lorentz force equation is no longer applicable because the velocity component is zero. So velocity component is zero. The force experienced by those charges, Q times V cross B, that is also equal to zero. So we cannot get back, we cannot derive our way from Lorentz force using Lorentz force equation to the Faraday's law that we have E equal to minus d phi by dt using that method. So we have to use the second equation, the second Maxwell's equation, the field equation that we have there, which is basically the curl of the electric field is equal to negative time rate of change of the magnetic field. Right. So using the Stokes theorem, we can rewrite this as integral E dot dl is equal to minus dou B by dou t. The group integral of the electric field is equal to the surface integral of the curl of the electric field. Right, so substituting the curl of the electric field here, we end up with negative surface integral of dou V by dou t times the surface integral ds. Changing the order of integration and differentiation around. So we have dou by dou t surface integral V dot ds, and this is essentially the flux. So we have minus d phi by dt. All right. So we end up with the same equation, and this is a one-dimensional case. So the integral of the electric field across the distance is same as the EMF E. All right. So we end up with the same expression that we had for our Faraday's equation that you had derived in your high school, that you have been given in your high school. But the Faraday's equation itself is not a fundamental equation, right? So it's one of those beautiful equations in physics where there are many phenomena like friction and stuff, where like for instance, static friction, rotation friction, sliding friction, we express different formulas for those, but underlying it's all the same electromagnetic theory, electrostatic forces pulling apart the charges that's preventing them from moving and so on and so forth, right? So in physics, there are many examples where on the higher level, there are multiple different phenomena, but on the lower level, they all boil down to a single equation or a single fundamental law of physics. In this case, it's rather the opposite. There is this very elegant, beautiful equation E equal to minus d phi by dt on the higher level, but it actually breaks down into two fundamental equations of physics, right? So the one is when the bar is moving and the B field is constant, it breaks down to the Lorentz force equation to explain the higher order equation that we have here. And in the other case where the B field is fixed, B field is varying, but the length is fixed, right? Lorentz force equation cannot explain it. We use the second Maxwell's field equation to describe what's going on, right? So both of those equations boil down into E equal to negative d phi by dt, right? So let's, before we proceed, let's look at the units for our EMF. So our expression for EMF right here was force divided by Q times eta L. Let me multiply both the numerator and denominator by the width of the bar. So force times the displacement through which the charge moves, the charge is experiencing this force, and it is displaced by this distance W. That is basically the work done. Right? And Q times eta L times W, I just erased it. That is the total charge across the bar. And that in turn is equal to same as the potential difference, right? So the work done in moving a charge is one of the definitions for how we can define voltage potential. So this is the reason that many a times, even though particularly we do not want to use the term voltage for EMF, it is quite often commonly called voltage because the units is exactly the same as the voltage. And in our case, for this two-dimensional case that we are analyzing, where the voltage potential can develop just across this one-dimensional bar, it really doesn't matter whether we are talking about it as a scalar quantity or a vector quantity, right? So in this case, it is pretty much non-directionless. So it doesn't really matter too much if you use the term voltage instead of EMF. But strictly speaking, when the curl of an electric field is not zero, it cannot be represented as a gradient of a scalar field. Right? When we talk about potential difference, we usually think of it as a scalar field. We talk about voltage at one particular point, and it doesn't depend on which direction you look at it from. The voltage is always going to be the same voltage. If at this point, if it's say 100 volts, and somewhere lower it's 50 volts, right? There's always going to be 100 volts irrespective of the direction I see it from. This point is always going to be 50 volts irrespective of the direction I see it from, right? And that kind of scalar representation for the field can be done. The gradient of such a scalar field being equal to the electric field is only possible if the curl of the field is equal to zero. Only then this is guaranteed. If the curl is non-zero, you would have to use vector potential, which we typically do not associate from our circuit theory course and stuff with the scalar potential that we have, which we typically call as voltage, right? So hence the discrepancy in the term that we use, but it's absolutely fine to, for our consideration to use the term differently, interchange the term as needed. Okay, so let's now clean out the two other equations that we have. So this equation disappears. So let's see, this is no longer needed. So instead, we have this rather elegant equation. E is equal to minus d phi by dt. Right? When you have a single coil loop through which there is a magnetic field, then the time rate of change of the flux through that loop is going to be equal to the EMF that's developed across the loop that we have. So again, this is not a replacement for just the second law alone, because there are two principles, both this and this, depending on the circumstances, whether the area is changing or whether the B field is changing. The Maxwell second equation or the Lorentz force equation could come into picture to explain the single equation. Right? But going forward, we're only going to consider it in this form, not worry about the other form. So also, in our course, we are not going to worry about the first equation either, because when we have our motors, in our ideal case where we are going to be analyzing our motors, there is going to be no charge differential. There is going to be no charge differential that's created across the motor windings or across the stator and the rotor and so on and so forth, right? There is no capacitive effect that we are going to be analyzing in our motor. So given that on a macroscopic level, even on a conductor level, there is going to be no charge difference. So that means there is going to be no electric field introduced because of any form of charge accumulation in the motor. All right, so this is not something that we are going to be considering in our course going forward. So the only three equations that we need are these three. And then we will rewrite the Lorentz force equation as well in a different form, where we'll put it in a form where it's the force experienced by current carrying conductor. That derivation we'll table it until next week. But for now, let's proceed with our current discussion. Right? So, and the Stokes theorem is also no longer needed. We have completely eliminated the curl expression, same as how we eliminated the divergence expression from our equations. Okay, so the next thing that we want to be looking at is what is the power that is going to be generated by this moving rod, or in this other case non-moving rod, doesn't matter. So this rod has some EMF that's developed across it. Right? So before we derive the derivation for power, let's address the question about the polarity of the EMF that's developed. So we have a rod, right? And we have charges on it. And as Kirnesh pointed out, when these charges are moving with some velocity v in a magnetic field B, which is perpendicularly outwards, it is going to experience some force which is going to move the charges down. Now I said that the U bar that is closing this rod, it can be a conductive material or a non-conductive material, absolutely doesn't matter. But let's say for this case, we are going to consider it to be a conductive material through which these charges can move around. So once these charges have been separated out, where the positive accumulates on this side, negative accumulates on this side, this bar now provides the conductive pathway for the charges to go back and merge again. So we have these positive charges that are going to travel through the conductive element pathway that we provided and then come back and close the circuit, right? So what Lenz's law says, what the negative sign essentially means is as I move this bar around, the B field, let's say the magnitude of B field is constant, but the surface area is increasing. That means the flux seen by this loop is increasing, right? What Lenz's law pretty much says is that the EMF is going to be generated in such a way that if you had to close the circuit so that the current can flow through the circuit, the current would in turn create a magnetic field that will try to oppose the change in the flux that's being created due to the motion of this magnet, due to the motion of this rod that I have. So what that means, as this rod moves, the flux seen by the surface area is increasing because the surface area itself is increasing, right? So the current is going to be created in such a way such that the magnetic field due to the current will try to now reduce the flux because the flux otherwise would be increasing. So let's see how that would happen. So the charges are now going to go through this way, come out in this way. So the same direction in which the hypothetical positive charges flow is the direction in which the current flows as well, right? And we can figure out what direction the magnetic field is going to be due to this current. Curl your right hand along the direction of the current, whichever direction your thumb points is going to be the magnetic field, right? So the magnetic field due to the current I flowing in the conductor is going to create a magnetic field that is going into the page. So the magnetic field that's causing the EMF is coming out of the page, and then the current is creating a counter magnetic field that is impeding the increasing flux that's seen by this loop as this bar keeps moving further and further. It could be the other way around too, where the bar is fixed, but the magnetic field magnitude itself is increasing. In the same case, again, the flux is going to be increasing, and the current is going to be set up in such a way, the EMF is going to be set up in such a way such that the current flows in this direction, so that it can create its own magnetic field that will try to reduce the increasing flux due to the external source. Now, if the opposite were to happen, if the flux is starting to drop or the magnetic field is starting to drop due to the external source, then the current would start to flow in the opposite direction so that it can keep increasing the reducing external field. Right? So basically, it doesn't want to change. So that is all this expression indicates the negative sign. So I usually do not find this too convenient. So I just draw it out, figure out what the force direction would be. And then the EMF would be such that whatever current is created, right, whatever current is created would be in a direction to oppose the change in the flux that's being seen. So in this case, where the B field is increasing or the bar is moving outwards, you would have an EMF with this polarity. If it were the opposite case, so either B is increasing or B is positive, right? If you have the opposite case where B is reducing, or the velocity is negative, or the bar is moving in this direction, right? Then the EMF developed across the bar would be opposite polarity. So that when you close this bar, a current would flow in this bar in this direction, curl your hand around, it's going to be creating a magnetic field due to the current, which is along the same direction as the external magnetic field. Because the external magnetic field is reducing, this added current would try to increase it so that it can stabilize the system. Now, if the opposite were to happen, excuse me, sorry. So if the opposite were to happen, it would be quite problematic. Let's say in the first case, as the magnetic field is increasing, the EMF was generated in the opposite polarity with positive on the top, negative on the bottom. Then the current would end up going in the anti-clockwise direction. Curl your hand around, the B field would be in the same direction as the external magnetic field, which is also increasing. Right? Now this added magnetic field due to the current that's going is now going to interact with this loop and create more force on this charge, which is going to further increase the EMF, which is going to further increase the current, which is going to further increase the B field, and it will become an infinite cyclical loop where it ends up going to a point where the current would become infinite. So you would have to end up, you put a limited amount of energy, but you end up with a case where you get infinite amount of energy, right? So it would defeat the conservation law, so that would not happen. So this is the only scenario, this is the only case that can play out in the system. So that's all the negative sign means. So you don't have to memorize it or try to remember it, just draw the system out and always put the EMF such that if you had to close the circuit outside, it should create a flux that would try to oppose the flux that's changing within the system that created the EMF in the first place. Okay. So with that, let's move on to figuring out what the power in this circuit would be. So I have this bar, there is some EMF developed across it, and we close this bar with some conductive circuit. There's going to be some current flowing in this bar. So everybody gave the answer that power is going to be equal to the EMF times the current. So we already said in this course, we are not going to assume any equations. We are going to either define them or derive them. We cannot define this because we have already defined power in lecture 3. Right? So power was defined as the time rate of change of energy, dW by dt, or work done. And then work done itself was defined as force times displacement. In our case, the displacement is the bar moving, right? The length through which the bar is moving. So the force times the displacement, which in turn is equal to force times, since the magnetic field in this case we are assuming it to be a constant, and the velocity with which the bar is moving is assumed to be a constant. This force is going to be a constant. Pull it out of the differential. You have dl by dt. That is just a force times the velocity. So we need to go from this map from the force times the velocity to EMF times the current. So let's start off by dividing both the left hands on the numerator and denominator by q eta L. Right, so this term we have already figured out is the EMF. So the derivation I just erased a while back. Right, so this is going to be the EMF. We are going to prove EMF E. We are going to prove now this is the current term. So let's try and do that. So this bar that I have here, right, we have some charges that are moving in this direction. I'm just going to rotate this and draw it in a horizontal fashion so that it's more familiar to our structures that we have seen before. Right, so we are going to look at a cross-sectional area of this bar. Let's say the cross-sectional area is some A. And then we are going to look at in time delta t, how much charges would move through this cross-sectional area. Right, I'm going to, so these are all the same positive, hypothetical positive charges that we are considering. Right, I'm just using different shapes for charges at different locations in the conductor. So after some time, so this charge at time t equal to 0, this charge is here. And after some time delta t, the same charge would have moved to this new location after some time t equal to delta t. So those charges would have come to this new location, the charges behind it would have come to this new location, the charges even behind that would have come to this new location, so on and so forth, right? And whatever was here in this section would have now moved to this section that's in between these two regions. So what would be the total distance covered over time delta t? These charges are moving with a velocity v, right? So charges are moving with some velocity v, and if you look at the total distance delta d covered by these charges, that is going to be v times the time it took for the charges to travel. All right, so once we have the expression for delta t, we can figure out what was the total amount of charge that is now occupying this area, this volume that we have here. So we define the charge density for this conductor as Q times eta L. Eta L is the number of charges per unit length. And Q itself is the magnitude of the charge. So this is the total charge per unit length of this conductor. So if this is the total length, what would be the number of charges in this particular volume? Basically multiply the charge density that we have times the displacement or the displacement that we have. So which in turn is equal to Q times eta times V times delta T. All right. So what does this indicate? It's basically after time t equal to delta t, how much charges is being accumulated between these two surfaces that we have here. Surface we started with first, and then the surface where we ended. In between, how much charge is accumulated? That is what this value indicates. This is also the same amount of charge that actually moved through this cross-sectional area that I've shown here. Right? Whatever was here, the charge is conserved in the conductor. No new charge is created. No charge is destroyed. So whatever charge is here was previously behind this cross-sectional area that moved through this cross-sectional area to get to this point. And whatever the charges that were previously here, that just moved from this cross-sectional area to another location, right? Completing the loop. So charges were now, no new charges are created. Whatever was here is just moving through this cross-sectional area. And how do we define current? Current is basically the amount of charge that moves through a cross-sectional area in a unit time. So our current is equal to delta Q divided by delta T, which is equal to, if you substitute these values, Q eta L times the velocity. Okay, so that is exactly what we have here. All right. So the next thing that we want to look at is, so far we have looked at very simple cases where we have a current carrying conductor and we looked at the magnetic field around this current carrying conductor. But we're going to complicate this a little bit further by looking at a solenoid. So previously we just had a simple current carrying conductor and figured out what the magnetic field around this current carrying conductor is going to look like. Okay. Next, what we are going to be analyzing is a solenoid. So a solenoid is basically, let's say I have an iron rod. Let's say I'm holding an iron rod in my hand. I take a copper wire and then tightly wind this copper wire very close together so that the turns are touching one another over this whole copper rod. That is effectively what a solenoid, over this iron rod, that is effectively what a solenoid is, right? There can be different cores in a solenoid. Typically you would use iron, which basically has a very high relative permeability. So in our case, we are going to start off with a simple scenario where there is no core in this solenoid. So I have this marker, I wind this coil around this marker, and I just remove the marker, leaving behind the coil alone. Right? So this is an add core solenoid. And we're going to try and figure out what the magnetic field of the solenoid is going to look like. So this is a three-dimensional structure, so it's going to be a little bit difficult to analyze. And we did say that we reduced it to all of these simpler equations because we are going to make all of the systems that we are going to be analyzing in this course is going to be on a 2D planar surface. None of them is going to have a 3D structure. So even when you have 3D structures like this, we are going to reduce it into a 2D structure so that we can analyze it using these simple formulas that we have re-derived. Right? So what we are going to do is take the solenoid and we are going to mathematically cut it right at the diametrical center and then analyze what the current structure looks like. So if I were to cut through half of it, right in the middle, then I can look at the top view of the system. So current is going into this side and coming out of this side of the conductor. So on the top side, the current is coming out of the page, which I'm going to indicate by this dot. And then it comes out of the page, goes in a loop here, and then goes back into the board here. And then it comes back out here, completing the loop backside of the board, and then comes up out of the board, goes back into the board here. So on and so forth, tightly packed, all touching each other. Right, so this is the equivalent 2D representation once we cut it and look at it just from the top view alone. So this is what we are going to analyze and use the formula that we have. Before we do that, there is a simplifying assumption that we are going to include, which is that the width of the solenoid is extremely tiny, right? And we'll see that why that becomes critical. Particularly, this must be much, much smaller than the total length of the solenoid that we are considering. So let's go ahead and analyze what this would look like. So we are going to start off with figuring out what the magnetic field looks like in between the conductors. All right, so let's zoom in on this two conductors. Okay, just to exaggerate them, let me draw them far apart. So the magnetic field due to this first conductor is going to look like this. Curl your hand around it. Right, so this is going to be the direction of the magnetic field due to the first conductor. And if you look at the magnetic field due to the second conductor, again curl your hand around it. Same anti-clockwise direction, the B field. Right. So since each of these conductors are basically a single wire, which are connected in series, right? Each of these loops are connected in series. So the magnetic field created by this and magnetic field created by this at a point equidistant from both of these is going to be exactly the same. So the magnetic field in between the two conductors are basically going to cancel each other out. Right? So this magnetic field is exactly the same as this, but just opposite in direction. So in between there is going to be no magnetic field. And the same extends for any vertical direction you want to consider. Vertical component of the conductor loop next to it would cancel out the vertical component of any magnetic field created by the loop adjacent to it. Right? And that only applies if these conductors are packed close together. If they are far apart, that doesn't apply because this is very far apart. The field created here by the conductor here would not be the same as the field created by this conductor over here. Right? This would be far more weaker. The blue one would end up being far more weaker than the black one that I've drawn here if these conductors are not packed close together. So that's a definite requirement where these are packed very close together. Right? And then the second one we are going to be looking at is the case of one top conductor and then the bottom return of the same conductor. So let's draw the magnetic field for those. So we have a conductor on the top and its magnetic field is in the anti-clockwise direction. Right? So for the conductor on the bottom, let's look at what the magnetic field is going to look like. We draw it close enough. And I'm going to consider a bigger loop for this. And since the current going into the page, it's going to be in the clockwise direction. So once again, if you look at the B field outside, they exactly cancel each other out. But if you look at the B field inside, the B field add up from the bottom conductor as well as in the top conductor. All right, so inside these B fields are in the same direction. Outside, the B fields end up cancelling it out. So when we look at the outside part of it and we say they cancel it out, it's only applicable if these conductors are close enough. Right? If these conductors are close enough, then the B field at some distance r due to the first conductor and the B field at distance same r due to the second conductor would be very close because let's say this is conductor 1 and this is conductor 2. B field at some distance r due to conductor 1 is going to be equal to mu naught I divided by 2 pi r. And let's say the separation between this conductor is W. Then the B2 at the same point, right? So this is B1. B2 due to the second conductor, this is going to be in the opposite direction, B2. That is going to be equal to mu naught times I, same current, but negative because the current is going into the page, so the current becomes negative, 2 pi r plus W, right? So this distance is r. The total distance from the second conductor would be r plus W. Now B1 and B2 are more or less equal if and only if W is very close to 0. So in our theoretical case, we are looking at a solenoid that's packed very close together, very tightly wound, as well as the thickness diameter of the solenoid is very, very thin. Right? So in those cases, we can then make this assumption that externally the magnetic field is going to be very close to 0. Not absolutely 0 because there's always going to be a difference because of the separation between the distance over which the thickness of the core. Right? So there's always going to be some separation which is going to make some difference present. But for our analysis, we are going to consider that B1 is equal to B2 and assume that the B field outside is absolutely 0. Okay? So there is a problem with that assumption. That will come back and bite us in a minute. But for now, we are blissfully unaware and we are going to march on forward. So we have a solenoid. Wrong color. And we have magnetic field only on the inside, not on the outside. Now let's go and figure out what the magnitude of this magnetic field is. So we have conductors on the top, conductors on the bottom. Again, it's not separate set of conductors, the same wire going in and out, in and out. We are just analyzing it in a planar form so that we can use the planar equations that we have rewritten our original equations from. So I'm going to draw a loop around this. Let's say the number of turns is n. And the current through the conductor is I, which goes here, comes out I all the way and comes out through this side. Right? So if I create this mathematical loop, we already showed there is only B field inside. Here the B is 0. Inside it's non-zero. Again, outside we just demonstrated that the B is very close to 0. And here again, vertical components, we already showed the B is very close to 0. In fact, it's much closer to 0 than the outside because these are very tightly bound together. So the separation between two consecutive loops, adjacent loops, is much, much smaller than the core thickness. So this would be very much more closer to 0 than the other component. Okay, so given the situation, now we can apply our fourth equation, simplified Maxwell equation that we have, which says if I go around the loop, integrate the B field, that must be equal to mu naught times I enclosed. Right? In our case, I enclosed is equal to the total number of turns times the current that's being going through each of these. So the number of conductors that are enclosed is n, and each of it is carrying a current I. So the total I enclosed is n times I. So how do we do this integral B dot dl? Well, these are all straight B fields that we have drawn here along the line. So the integration is pretty straightforward. Let me call this B1, B2, B3, B4. Let me call this loop's length L1, L2, L3, L4. This loop can be of any size. The only requirement is that some of it go through inside the solenoid because that's the B field we are interested in. So if I do this integral, that is just equal to B1. Within this, the B is the same because all the conductors are carrying the same amount of current. So it's going to create the same B field at every single point, more or less. So B1, L1 plus B2, L2 plus B3, L3 plus B4, L4 must be equal to mu naught n times I. Now this term is 0 because B2 is 0, B3 is 0, B4 is 0. Only term that survives is B1, and L1 itself is the length of the solenoid. So let's call the length of the solenoid as L. So this is just L. So the B inside the solenoid is just equal to mu naught N I by L. Right? So that's going to be the magnetic field inside the solenoid. We are in quite a bit of a problem here though, because we have created essentially what's a monopole now, which we said is not possible. There have been no observations to indicate that monopoles exist. There was some observation back in, I think, 1980s or 1970s by some European physicists, but that could not be reproduced ever again. So as of now, our understanding is that monopoles does not exist, magnetic monopoles. So, but in our case, what we have is, we have these field lines B inside the solenoid, but outside we said the B field is 0. Right? So what then I can do, I can create a surface like this, right? A closed surface, so that B field is always leaving out of this closed surface, but nothing is coming back inside. Then the surface integral, closed surface integral, B dot ds is not equal to 0 in the case the way I've drawn it. So that's a problem because it's violating the fundamental laws of physics, which is not possible. So what we missed is, in the case where we analyze the B field outside, it is very close to 0, but it's not 0. So the field lines always close. It is just that inside the field lines are concentrated, but outside they have the whole world to spread around before they have to come back in. Right? So the flux in both the cases are the same. Flux leaving this surface is the same as all the flux that's coming back inside. Right? But the B field, on the other hand, is not the same. So, for instance, for example, think of a pipe carrying water. So, let's say we have this elaborate apparatus. And there's some kind of pump here that's pumping the water. So water molecules pass through this pipe and then go here and then come back and loop around all the way back, right? Let's say we have created this apparatus just for like some art installation or something, where we have this water moving around. All of us know intuitively that inside this tiny outlet, the water is gonna have a huge amount of velocity compared to outside, right? Because outside here, there is a lot of space for the water to move through. So the amount of water, the volume of water moving through this tiny cross-sectional area at any given time must be the same volume of water moving through this cross-sectional area, assuming an incompressible fluid, right? But in this case, the volume is extremely large. The pipe outlet through which the water can flow is very large. But here the outlet is very tiny. What that means is here, even though in both the cases, our velocity at which the water is flowing times the cross-sectional area V1, A1, A1, A2, and V1, A1 is equal to V2, A2. Because the volume of water, the rate at which the volume of water is flowing through this, if it's say 1 liter per second is flowing through this, same 1 liter per second is flowing through this as well, right? But the cross section that's available for that amount of water to flow through is much tiny, so the velocity has to be extremely large, right? So that the volume, the rate at which water is flowing through both cross section can end up being the same. We have the same system here. So here, the cross sectional area inside the solenoid is this coil area, A1. And the B field inside, let's call it B1. But on the outside, we have the whole space available. Right? Let's call that A2. And the B field due to that being B2. In both cases, the flux that's leaving outside must be the same flux that comes back in. So the flux here must be the same flux over this full cross-section area, starting from the top, going all the way to infinity, and same starting from the bottom, going all the way down to negative infinity. Right? So B1, A1 is going to be equal to B2A2. Because this law cannot be violated. This always has to be equal to 0. Fundamental law. So what that means is, outside of the area is very large, then the B2 can be very small and still satisfy this expression. So this goes towards infinity. This can go towards 0 and still satisfy the condition B1A1 equal to B2A2 for flux to surface 1 must be equal to the flux to the surface 2 or the remaining surface of a surface. Right? So this will always be guaranteed because it's a fundamental law. But that also means that we can also do it because the B2 is tending towards 0 when A2 is tending towards infinity. And that's exactly what we said here. Right? B1 is roughly equal to B2, negative B2. Right? When we have those conductors placed very close together, the B1 here and B2 here are roughly equal to one another, just opposite in polarity. Right? They are not exactly equal. If they are exactly equal, we will end up creating monopoles, which is not feasible. So since they are roughly equal, there is a tiny portion of the B field that's still outside. But for our derivation, when we derive the magnetic field inside the solenoid, when we consider just one loop, when we derive this, we are just looking at one single loop. Right? We are not looking at a full cross-section area going all the way to infinity and then integrating. If we did the surface integral, the flux inside would have been the same as the flux outside. Right? There is no other option. But when we look at this loop, the B field of this loop outside can be approximately assumed to be 0 because that's exactly what we proved. The flux is exactly the same, but the B field will be very tiny and negligible. So we can go around the loop, integrate, we can ignore all the other components as they are very close to 0 and only the inner component alone matters. Okay. With that, let's end today's lecture. So I also mentioned, those of you who are looking at the video recording later, in fact, I mentioned that I have to do the last 2 problems of the homework 3. We need to derive some more content for inductance and energy storage and inductance before you can address homework problem 3 and 4. Table that for now, just do homework problem 1 and 2 in homework 3 for this week, and then with next week homework 4, you can add the other 2 problems as well to your homework. Right? With that, we are done. We'll meet on Thursday. Thank you.